So how difficult is this to implement? Not very difficult at all. So here's our hash function, and let's say we randomly generate our IP addresses. So this is a single IP address in this case. How do we create our hash function? We're going to randomly select coefficients for our hash family. We're going to pick 4 values at random. Each one of those is in the range 0 to n-1, inclusive on both bounds. And then here's our hash function, the dot product modded by n. So when you run this, you can get an IP address that looks something like this. Your hash coefficients look something like this. And your hash value is always guaranteed to be in the range of the number of buckets you have. Now, how can you create a pathological data set for this? Well, the only way to do that really is to predict what our hash coefficients are going to be. And if we seed our random number generator appropriately and we don't let somebody know how it's seeded, there's no way for somebody to guess what those values are and sort of make use of that information. Alright, so let's go back to whether or not the family we just created of hash functions is universal. So here's our theorem. This is what we want to prove. The family H is universal. And again, what is our family H? It's this. It's all hash functions a.x mod n, where a are some randomly generated values. Each one of those values for a is in the range 0 to n-1. So, I'm not sure why this was showing up yet, sorry. So let H be the set of hash functions that we have. The family H, again, is going to be universal if and only if the probability of a collision among any two items for any randomly chosen H is less than or equal to 1 over n. And again, another way to say that is that the number of functions that map x and y to the same location, out of all the total number of functions, which again this was 988 billion, so the number of functions we have up on the numerator here, we have to show that that's going to be less than 988 billion divided by n. Another way to say that again is that we don't have a lot of hash functions that commit the same problem, so the same collision between x and y. So how do we prove this? So let's work through our proof here. Let's consider 2 distinct IP addresses, x and y. We're going to assume that x and y are not the same value. If x and y are the same value, then they're always going to map to the same location. So if x is equal to y, then this number ends up being 988 billion over 988 billion, which is not less than 1 over n. So that's not really very interesting or useful, because we hope that that's the case, that all hash functions map the same value to the same value every time. So we're going to assume that x and y are distinct, and we can assume that in any different possible way. For now, we're just going to assume that they differ in their 4th values. So we have x1 dot, let's do this differently, x1 dot x2 dot x3 dot x4, and those are the actual periods that show up when you write out an IP address. That's not the dot product in this case. And then we also have our IP address y, so that's y1 dot y2 dot y3 dot y4. They can differ in any way. What I'm saying here is that let's just assume they differ in their x4 and y4 values. So it doesn't matter if this is 10 and this is also 10. This is 16 and this is also 16. This is 12 and this is 12. As long as this one is, for example, 25 and this one's 26. We're just going to say they differ at least in their final parts. And it doesn't have to be x4 and y4. It could be any of the values. We're just going to take the last one for the sake of this argument. Based on our choice of a hash function, and again it could be any of the 988 billion, what's the probability of a collision? So how many of our hash functions collide the x and y IP addresses? So, and that's for any of the h. How many of our lowercase h's from our family of uppercase h's collide those two values? And what we want to show is that less than or equal to 1 over n of those billions of hash functions have the same collision. Alright, so again, this is what we're trying to show. For any possible hash function, the probability of a collision between x and y is less than or equal to 1 over n. We're going to select out a hash family, or we're going to create a hash family by randomly generating 4 values for a. And then we're going to say, what's the probability of this? That the hash function on x equals the hash function on y. So that's a collision between those two. What are the hash functions? Well, in this case, it's just a dot x and a dot y. What are the chances that those two things are equal? Well, I can split out the a dot x and y into the actual equations for those. So a1x1 plus a2x2, etc. And, well, we know, before I jump ahead there, let's move everything to one side of the equation. So I'm going to move everything over to the right-hand side, and I'm going to group like terms. So if you notice, we have that a1 is multiplied by x1 here, and a1 is multiplied by y1 there. So I'm just going to group those two terms together. We know that something must be different between x and y, and just like on the previous slide, we're going to assume that the only difference between these two IP addresses is x4 and y4. So we can move that back to the left-hand side. And this is our current equation. So this is how they differ. And all these terms over here are potentially the same. Or at least fixed. Let's assume that n is a prime number, and we'll come back to why assuming n is a prime number is required for this later on. And so what we have here on the left-hand side is some fixed non-zero number. N is a fixed number, a4 is some fixed number, x4 and y4 are all some fixed numbers. So we have some fixed number over here. Let's also fix our choices of a1, a2, and a3. On the previous side, I apologize, I made the mistake of saying that a4 was a fixed number. We're actually going to let that remain to be a random number. How many values of a4 satisfy this inequality here? Alright, and since I kind of made a mistake with that explanation, let me just recover that again. We know that this is a fixed quantity, this is a fixed quantity, this is a fixed quantity, n is a fixed quantity, and it's a prime number. We're saying now that let's fix a1, a2, and a3. This is a fixed quantity, and we're going to say that a4 is a random variable. So why can we say that a4 stays random while a1, a2, and a3 are not? This is a property called the principle of deferred decisions, and it's essentially what it says is it doesn't matter what these are going to end up being. We can still choose a random a4 for any possible combinations of a1, a2, and a3 and still end up with the same argument. Okay, so again, let's go back to this question here. How many choices for a4 satisfy this equation? Well, we know that the right-hand side is fixed because everything over there is fixed. So that's just some constant. And we know that n is a prime number. So why does it matter that n is a prime number? This is where this is finally going to come into play. If n is a prime number, that means that the left-hand side is equally likely to be any value from 0 up to n minus 1. When you take anything mod in n where n is prime, that's a quality of prime numbers. That does take some number theory to prove, and that's sort of out of the scope of what we'll talk about in this course. In the next video, though, I'll just demonstrate to you. It won't be a proof, but it'll be sort of a demonstration that this works on at least an example. Okay, so now we know that this value over here is any value in the range 0 to n minus 1. And we know that this value over here is some constant c. So what that means is only one value out of these n choices over here, only one out of these n is equal to c. So based on our choice of a4, we've proven that the probability of a collision between these two is just 1 in n. And it turns out, 1 in n is in fact less than or equal to 1 in n because they're equal.